Then I might bring it back and we can use it as bribes for the rest of the course. So does that sound like a good idea? Thank you very much. And remember, that was for this side doing a good Mexican wave. So you guys need to thank these guys. So oh, good. Well done. Excellent. All right. Now let me just take a second. Luke, one of your stew reps, said he's put a poll on the forum to find out what things people are finding hard. I think that's really good. So anyone that's finding something hard, please either tell the stew reps or any of the stew reps, whose names I haven't put up, I don't think. So the stew reps, could you make sure you put your names on the forum somehow or get your tutors to contact me? I don't know how I forgot to do that, I'm sorry. Who are the stew reps? There's Luke and Dane and I can't remember her name. Because she was the only girl, so we didn't make her stand down the front and humiliate her and say her name over and over again. Who is it? The other stew rep? Wave at me. She's not here. Oh, no, that's all right. That's all right. I'm just being silly. It's quite fine to not be here. But could you guys please contact these people if you're finding anything hard, tell them, and then I'll know what's hard. So we've done. I'm just typing while we're talking. We've done everything I wanted to do. Oh, you can't see, sorry. Revision from Tim. The importance of getting a good spec in advance. Shh. Please make sure always the spec is tied down. I remember my first private consulting job was in the evenings. I wrote programs for another company while I was working full-time for one company, but another company needed one job done in a rush. And they said, could you do it? And I said, okay, because I figured I had some time in the evening. So I used to work really hard at my normal job. Then I'd come home in the evenings and work really hard on this contract job. And I wish it was a contract job. They just called me into the office and told me what they wanted. And I didn't get them to write it all down. And I should have got them to write it all down, then cut their hands and get a bit of blood and spit on it and rub it in and say, I vow this is what I really want you to do. So I spent an enormous amount of time writing the program and I brought it in and showed it to them and they said, oh, that's good, but now we think about it some more. That feature there and that feature there aren't so important, we don't care about them. You know, I'd spent a whole week trying to get them working. And this bit here, I don't think we explained that. We really wanted to do this. Oh, no, they didn't say that. They said, we explained it, you didn't understand. This has to do something else. So I said, oh, tell me exactly what it's got to do. They told me, I went away and wrote it again. And it was like this. For the next couple of months, it was hell on earth. Every time I'd go in and show them what I'd done, they'd say, that's good, but can you change this? And because I hadn't got them pinned down in advance saying exactly what I had to do, this was for a fixed fee, I was like their slave for a while, until eventually I bought myself out of service and escaped. So make sure you get the spec pinned down in advance. Now we're going to write a Sudoku. Does everyone know, some people call it Sudoku. Sudoku. There's so many ways you can play with O's and U's in this. It's very exciting. Sudoku, I'm going to say Sudoku. A Sudoku is, what, it's like 9, oh, yeah, I remember. Okay, hang on. It's got like 9, what do we call these things, little boxes. It's got a big grid, which has got 9 boxes in it. And each of these little boxes contains 9 cells. It's a bit like that Going to St Ives song, isn't it? So, on the way I met a box, and every grid had 9 boxes, and every box had 9 cells, and every cell has one of 9 possible values. Every cell can contain either 1, 2, 3, 4, 5, 6, 7, 8, or 9. And the rule for Sudoku, for a legal move, you have to fill the thing in. When you filled it all the way in, you've won. Let's call each filling in a move. To make a move legal, this is completely empty, so I can write whatever I want in the middle here. So I'm going to write a 1 here. Now, the rule for Sudoku is there can be no other 1s in that same row. And there can be no other 1s in that column. And there can be no 1s in this middle box here. Does that make sense? Now, you normally get it with a thing half filled in, and you've got to fill the rest of it in. And if it's a good puzzle, there's normally only one way of filling it in, and you've got these few little clues. So you're always going, I could put a 2 in here. Oh, bugger, there's a 2 up there. Oh, what if I put a 6 in here? And then later on, okay. It really wastes hours and hours playing this amazingly annoying game. How nice it would be to have a computer program to solve it. So let's look at how to solve this. Do you know that in the first couple of weeks, I made you do things like estimate the number of blades of grass in the university and the number of grains of sand on a beach. I could now ask you how many ping pong balls it would take to fill this room, how many ants you could fit on a bus, one of the uni buses. This is called estimation. Why did I get you to do estimation? Estimation is probably going to be in the final exam because I really want you to be able to do estimation. Why? Anything in the tutors and labs is probably in the final exam. Why do I want you to know how to do estimation? What's cool about estimation? Look.
Maybe just estimate how long things are going to take you when you're writing code.
Oh, we have to use estimation as a practicing programmer. Yeah. Not only to estimate how long it's going to take to write the code, though that's an important thing to do. Yes?
Estimation is interesting. It's a bit abstract. It's not an exact answer.
It's not an exact answer. It's abstract. Yes.
You can see a graph which says semi-realistic.
Yes, that's it. Okay. In computing, we have to deal with large numbers. Often, frequently. Either our program does a large amount of work, or uses a large amount of memory, or it's literally dealing with large numbers. We need to have a rough feel for how big those numbers are going to be. We need to know if they'll fit in an int, or we need a double, or a long, or so on. In the old days, like in the Viking days, they could count up to 1. I had to invent the word million. What did I call it? I called Miljon or something lame like that. The Vikings didn't have a word for million. Why not? They didn't need that word. They had, I killed 2 villages. I killed 50 villages. None of them could ever kill 100 villages or 1,000,000 villages, so they didn't need words that big. So I imagine their idea of counting was like, we did all these fancy words, but I imagine it's like 1, 2, 3, 4, 5, 6, 7, blah, 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 up to their 1,000, their Thurston deer or whatever they call it, and then they'd go, a lot. Okay. How much gold did you bring back? Oh, a lot. Because they didn't need those numbers. And in everyday life, we don't really need big numbers either, though these days we need million a bit more than we used to. So we are really good with estimating small numbers. You know, if I had to ask you how many people are in this room, you'd probably have a reasonable guesstimate. It's a couple of hundred. It's like somewhere between 1 and 200 maybe. It's not 1,000 and it's not 20, because we're familiar with all those numbers.
56 minus how many miles?
Well done, Stevie. We can calculate exactly how many people are in the room, unless someone. Well, yeah, okay. So in our everyday life, we also are not. We're perhaps more familiar with big numbers than Vikings, but we're not awfully familiar. And in fact, I was at a meeting at our school recently, and someone was talking about how many hours one of their PhD students spent on some job or something. And when they said that, there was this like silence in the room for a second, and every single person in the room, I bet, or every single engineer that was an engineer in the room, was taking that incredibly large round number the person gave and dividing by the number of days the person had been working on the job. And we discovered that that person had been working 25 hours a day. Because they all had a feel for large numbers, and they had a feel that that number was too large. But in fact, there's a really amusing book you can get called How to Lie with Statistics. And the person in that book who writes that book claims that most people's brains numb out for big numbers. And you can tell them anything ridiculous you want, and people will believe it. So if I said to you, Australia uses, actually burns out 3 million incandescent light globes every year in a newspaper story, would you believe that? You probably would. And if I said we burnt out 30 million, would you believe that? And if I said we burnt out 300 million, would you believe that? And if I said we burnt out 3 billion light globes a year, would you believe that? One of those answers is right. The others are orders of magnitude wrong. You could perhaps be a little bit uncertain about it. In this book, How to Lie with Statistics, that you should all get, the guy claimed you could say any ridiculous number you wanted and people would believe it. Challenge to you, how many incandescent light globes do you think Australians burn out? It gets used up in a year in Australia. I think it's more than 3 million, by the way. So I want you to have this skill, because I want you to be familiar with large numbers, because we use them all the time in computing. And if you can't tell the difference between a million and a billion, because both of them you think are a big number, you're stuffed. Because a million and a billion are completely different numbers, and they have completely different properties. And if your program has to do 1 million things, you're okay. And if your program has to do 1 billion things, you're in a little bit of trouble. And if your program has to do 1 trillion things, you start to get really worried. And they're not all the same. They're completely different. One of them can be done in a few seconds, one takes maybe a few days, and one takes maybe a few years. Okay, so we need to have this facility for dealing with large numbers. So I wanted you to estimate to get the feel for large numbers. But the other reason we did estimation was exactly the reason someone said, I can't remember, one of you guys, was abstraction. The neat thing about estimation is to do estimation, you need to do problem solving. The key with estimation isn't, if I said how many ping pong balls would fit in this room, if you just say a lot, that's not solving the problem. If I gave you a small thing and said how many ping pong balls could fit in my hand, you'd probably say like 2 or 3. You can solve a small problem, but if the problem scaled up and you don't know how to solve it, you're stuffed. Now, solving problems in computing is exactly the same as this. We have big problems we have to solve, and we need to know one thing to solve those problems. We need to know what is the most important bit about the problem. Given any problem, given any murder mystery, given any design you have to do for school, given any recipe, given any piece of clothing you're manufacturing, given anything you have to do, there's normally some important bits that you have to get right and some less important bits that aren't so important. And a master craftsman or tradesman instantly knows what are the important things and gets them right and doesn't worry too much about the other things. And a novice worries about every single little thing, wasting way too much time on the unimportant things and not enough time on the important things. And estimation is exactly that. If I asked you to estimate how many ping pong balls are in this room, or how many ants it would take to fill a bus, you can get the answer a little bit wrong. You don't have to get the details right, but you have to be able to abstract away all the irrelevant things and spot what's important. Yeah? Solving a problem is exactly like that. So we now have a big problem to solve, which is how are we going to write a Sudoku solver? And we've got 3/4 of an hour to write a Sudoku solver. We could do the low-level approach and just think about all the details and get bogged down in details. But there are so many details we're dead. If we sat down to try and write it that day, we'd never solve it. A master programmer thinks, okay, I've got the problem. And the first question they ask themselves is what?
How long will it take to solve?
No, let's just hope we can solve it in time. The key thing in solving the problem, yeah, I mean, we should check that it is feasible to solve. I believe we can do it in 3/4 of an hour.
How do we know we solved it?
How do we know when we've solved it? Yes, that's a good question. You guys are both being really specific, and they're possibly the questions we should ask.
It's sort of generally, like how should we go about solving it?
Yeah, how should we go about solving it? The most important thing when we get a problem is working out what is the most important thing. I now have to go through a process of solving this problem. What is the key thing? What are the most important things? If I get the most important things right, maybe the most important things are I don't have enough time to solve the problem. I've got to think about that. Maybe the most important things are, what was your one?
How do we know we solved it?
Oh yeah, maybe the most important thing is like with the Viking problem. For me, when I looked at it, the most difficult thing about that problem was, shit, I could write a program, it could look completely correct, it could print out a whole lot of gibberish with J's in it, it could be correct for all the small numbers I test, and it could be utterly wrong everywhere else, and I could just never know. For me, looking at that problem, the most important thing was how do I know when it's correct? With Sudoku, what is the most important thing? So I'm thinking now, as a good designer, there might be 2 or 3 most important things. There's a whole lot of irrelevant things as well. Now, human nature being what it is. Have I told you the story about the hang glider? We're using up our 45 minutes. But this is the most important thing about the lecture. I was learning hang gliding. I was just thinking I was going to be so cool and learn how to hang glide. So I was doing it, and I was asking the guy nervously, you know, what can go wrong here? And he said, look, really, everything's fine until you land, and then possibly you could die. And I said, oh, okay. What are the problems with landing? And he said, well, more or less, the main problem is if you land and you hit a tree. You know, you're coming down smack into a tree. That could hurt you. That's why we have helmets on. And I said, oh, okay, so I just got to avoid trees. And he said, yes, but it's not as easy as you think. He said, because, you know, I've seen novices come down in a paddock, a completely empty paddock with 1 tree in it. And they just, and boom, hit the tree. Have I told you this story before? Because it was struck when he said that to me, I thought, oh shit, that's true. Because I was so nervous about learning how to ride a bicycle, even though I love them and ride them all the time now. And my neighbour, the nice lady next door, said, ride Susie's bicycle, her daughter's bicycle. You can learn on that. You'll be fine, everything will be okay. So I got on Susie's bicycle and I headed off. Her backyard was completely flat and empty of all obstacles except it had a Hills Hoist in the middle. I pranged Susie's bike into the Hills Hoist and damaged it. So, hey, someone took one of my big Mars bars. Oh, man, that was a gift to me from a really nice student. Someone stole it. Oh. Luckily, I have a magic box that can duplicate Mars bars. Okay, it's getting there. I think it's the same thing. I asked the guy, why do people crash into the tree in the middle? And he told me it's the same reason I crashed into the Hills Hoist. Because the whole time I was on that bike, I thought, I hope I don't crash into the Hills Hoist. I don't want to damage Susie's bike. I hope I don't want to crash into the Hills Hoist. So what was I doing the whole time? I was worrying about the Hills Hoist. And because I was worrying about the Hills Hoist, what was I doing with my body? My eyes were looking at Hills Hoist. My head had turned towards, my shoulders twisted towards. With a hang glider, you're coming in, you're thinking, I don't want to hit that tree. And you're looking at the tree, and your body lines up. And if anyone, has anyone here a hang glider? You sort of steer by pointing your body and looking at where you want to go. So I think it's the same with this problem. The danger with this problem is we're going to think of something and we're going to start thinking about that thing. And we're going to, like the hang glider, we're just going to head towards what we're thinking about. So the thing with Sudoku is I think probably we're going to sit down and we're going to think, either if you haven't programmed before, you're going to get really nervous and think about the hardest bit. And if you've already programmed and you're thinking this is exciting, because you can already do the syntax stuff, you're thinking, what's the most interesting bit? So we focus on this. Let's pretend we're focusing on the most interesting bits. All we can think of is, gee, how can I solve a Sudoku? And we start thinking about all this really elaborate, detailed, fancy ways of solving it. And what if there, and I know that, and I can use this double, triple rule. And we think about all the fancy things. And we're going to spend all our time thinking about this fancy stuff. And the three-quarters of an hour, or now less, is going to be up, and we're going to have nothing. Because we'll have just been thinking about the fancy, irrelevant stuff. The key thing, I reckon, in solving a problem like this, so now, I mean, we have to work out what the key thing is. It's not thinking about the fancy stuff. It's not thinking about the fun stuff. It's not thinking about the stuff we're frightened. We've got to work out the most important stuff. For me, the most important stuff in solving any problem, and computer science is increasingly moving this way over the years, in the old days when people saw a problem, they used to think the most important thing was, is there a cricket or what is it? What is it? It's a cricket. There's actually some life. Wildlife. Oh, this is beautiful. If someone could bring plants in next time, we could slowly transform this barren concrete thing into a lush jungle. It would be incredible. Hong Kong was like that. It was just amazing. High density buildings, next to them beautiful mountains covered with greenery. Like this crazy mix of density and beauty. We should learn from that in Australia. We just got like uniform grey everywhere. They had, you know, it was just, no matter where you were, you could see something beautiful, like Central Park. It was very nice. What's that? Have I flown over Sydney? Yeah, there are green bits. There are green bits. Not in the suburb I live in, sadly. But yeah, in the North Shore there's green bits. And there's a beautiful park in the middle that hasn't yet all been turned into parking space. Okay. Shh. Over the years in computing, people have stopped thinking about we've stopped thinking about the algorithm. The algorithm is like, I'm going to get it to do this, and I'm going to get it to do this, and I'm going to get, and you're thinking about the flow control. You're thinking about all the stuff you're going to get it to do. You're thinking about the sequencing. And people have realized that this is the least important part, and we shouldn't really worry about that. Look, I do sometimes teach, and other times a guy called Alex teaches, who's absolutely amazing. A course called Algorithms in third year, where you'll learn all the beauty of algorithms, and they are truly beautiful. But normally the algorithm is not the key to the problem. Normally the key to the problem is in fact not on what you're going to do, but what you're going to do it to. Normally the key to the problem is your data, and how you arrange your data, and how you structure your data. Structure. And we call these data structures. And in the early days of computing, there were no ways of organising data. It was like our 8-bit machine code. Everything was just an int. It was just like a number. And then C and languages like C were around, and we had ints, we had floats, and we had doubles. And then someone thought, oh, what about arrays? What if we want to have multiple aggregates of data? And then other forms of data. And then more and more languages came on. And as every new language comes on, and C was a very early language, really nothing happens in terms of the expressiveness of the language, in terms of the algorithms. You get very few new commands or anything. You get no new flow control. Everyone's just loops, ifs, and function calls. This stuff doesn't change the same. What changes to make new generations of language better and better is they get more and more sophisticated and fancy ways of dealing with the data. And it turns out that by moving as much of the complexity into the way you structure your data as possible, you save yourself a lot of pain. So in this problem, the very first thing I'm going to think about, before I think about any of this stuff, this is a tree that's asking you to waste all its time on, I'm going to think about getting the data structures right. And once I've got the data structures right, this is all just going to come really easily as the second thing. It's just going to be like a whole lot of trivial steps. The problem's just going to melt away before you even get to it. So the data structure is, how am I going to represent a game? So how am I going to represent a Sudoku grid? Now, yeah, I mean, array is probably our only option because it's the only interesting data structure you've learnt so far. I'm just looking for an eraser. Eraser. Yeah. Oh. How about that? And look, I can also, it's a pointer as well. Wow, it's like so useful. It's like a Swiss Army knife. Okay, yeah, now look, we got this grid. I drew it and then rubbed it out, it looks like. We've got this big grid made of boxes, and the boxes are made of cells. I could store it as 81 variables, yeah, A1, A2, A3, but that's useless. It's going to be indirect addressing is going to help us a lot, so I'm going to store it as an array. There are other ways of storing it. There are better ways of storing it, but at the moment we can only store it as an array. Now I could store it as a two-dimensional array. I could store it as an array that I specify an x coordinate and a y coordinate, and that picks out a cell. Yeah, that would be a two-dimensional structure. You can have two-dimensional arrays in C, though they are slightly icky in C. But I'm going to instead store it as a one-dimensional array. So how am I going to store it? How am I going to structure the data? How am I going to represent a Sudoku grid?
X plus Y times.
So I'm going to have an array. How big is the array going to be, probably?
81.
It's probably going to be 81 long. From 0 to 80. And how am I going to fold this array, this line, over this grid? I'm probably going to zigzag it across. What do you think of that? Does that seem reasonable? There's lots of ways of doing it, but let's just pick one. So I'm going to zigzag the array across it. And what am I going to, so the first 9 cells are going to store this first row, and the next 9 cells are going to store the next row, and the next 9 cells are going to store the next row, and so on. So to think if things are in the same row, I just have to add and subtract 1 to move along. To think if things are in the same column, what do I have to add on? I have to add 9 on because the address below is 9 higher. To think if things are in the same box, that's a little bit harder. That's going to be the icky bit. Straight away, that's our tree asking us to crash into it. So I'm not going to think about that now. Don't worry about that. That will come. Don't start fretting about how you're going to represent the boxes. So we picked our data structure. What are we going to store in here? Ints, chars, what? Ints would be cool. What values can be stored? Bytes would save memory, yeah?
0 to 9.
We need to store 0 to 9. Why zeros?
Blank.
Well, can I say we need to store blank and 1 to 9. Now maybe we're going to say blanks are zeros and maybe not. For ease of printing out and reading in, I'm actually going to be lazy, and I reckon I'm going to store this as an array of characters. And I'm going to represent 1 to 9 as the characters 1 to 9, and we're going to use a particular character to be the blank character, the blank value. So we're going to have a cell, the address of a cell is going to be a number between 0 and 81. So I'm going to say typedef typedef int is a cell. So whenever you see the word cell, it means int. So cell is what I'm going to use to refer to the cells in here. The values, well, I'll call them values. I'm going to go typedef char is going to be a value. And then the whole grid is going to be a type. I'm going to call it a Sudoku grid. So I'm going to go something like typedef, what's it going to be? An array of how many? Array of what? Array of values. So it's going to be array value Sudoku grid 81. So whenever you see Sudoku grid, it means an array of 81 values. And I'm going to actually not do it on the blackboard because that's too hard. Let's start typing. And I did grab a few seconds while I was setting up there, and I have typed some of this stuff in already. Let's have a look. I put in as much as I could squeeze. Still not much, but I reckon we'll be right. You can't see it? All right, last time we worked out the magic way of fixing that. Okay, so here's what we got. The min value is 1, the max value is 9, empty value is dot. The number of values is going to be 9, the difference between the min and the max plus 1. The grid size is the number of values times the number of values, so the grid size is going to be 9 times 9, which is 81. And the maximum coordinates of a cell are 80. The biggest cell is 80. These are all the numbers that I could think of that we might need to use. And the main function is going to simply... this looks probably better than it is. Really, it doesn't actually do anything. The main function is declaring something called sample, which is a Sudoku grid. And remember, we type-def Sudoku grid to be... Oh, we haven't type-defed it. Oh, bugger. OK, let's do that. So we need to go what? Type... Oh, thank you very much. Type-def... type-def... char value... type-def cell to be an int. Oh, I did it backwards. I always get it backwards. I mean, C is... it plays this little game. Cell and type-def Sudoku grid values. Oh, I've done it backwards, thank you. Always do it backwards. Sudoku grid, and what's the grid size? Oh, it's called grid size. Oh, thank you. Doesn't understand plurals. Okay, so now we've defined our type. Okay, that's why I was getting compile error before. It didn't know what Sudoku grid was. So this here, Sudoku grid sample, means it creates a variable called sample, which is of type Sudoku grid. Now I know Sudoku grid is something else. We've defined it to be an array of blah, 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 blah. But for solving this problem, that's irrelevant. I wanted to give it a name so I can think of it as a Sudoku grid. And I wanted to think of the value, I wanted to give the value a name, calling it value, so I can think of it as a value. I'm no longer going to be thinking about these basic types that C has. I'm thinking about these more abstract types that I'm inventing myself. And I'm going to solve the problem in this high level way. Hey, the guy's over there talking. Shh, 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 shh. Okay, so we defined one, then we're going to read in the game somehow. It's going to read it in from the command line. We're going to have to write something to do that. So it's going to read in the initial grid. And then we're going to write a function called hasSolution. HasSolution is going to be given a grid, and if it has a solution, it's going to return true. And if it doesn't have a solution, it's going to return false. And if it has a solution, we want to print the solution. And we're going to have a function called showGame to print the solution. Whew, which we're also going to have to write. Sounds a bit scary, doesn't it? What's happening here? This has solution. It's obviously returning what? What type is it returning? True or false Boolean, which is represented as an int. So it's returning an int. But we're showing the game immediately after running has solution. Isn't the game just something we read in, the initial game? Isn't this going to show the initial game again? No, because we're going to need to change it. We're going to change sample. How is hasSolution going to change sample? By reference. We're going to use it by reference, because sample is really what type? An array. It's passed into the function. The function is allowed to fool around with it. Remember we looked at that? Arrays are always passed in by reference. So this function is a naughty function. It does two things. It both returns a value, which is true or false, to say whether it has a solution, and it also updates sample to be the new solution. It does two things. Doing two things is very complicated. It's best to just do one thing at a time. In this case, I needed to do two things at a time. Sometimes you just have to do two things at a time because the task is so long and complicated, and at the end of doing the task, you know two pieces of information, and you really want to return both of those pieces. Like, for example, I could try and solve it, and if I eventually get a solution, then yes, I know it's solvable. And I also, at the same time, know what the solution is. It would be insane if I wrote an is-solvable function that said solve it, and if you're able to solve it, print yes, otherwise print no, and that's all it did. And then I had to write another function to actually go and solve it, to print out the solved version. Then I have to solve it twice to both answer the question, is it solvable, and to see what, does that make sense? I don't want to do a big job twice, so in this case, it sort of makes sense. I hate doing it, but it sort of makes sense. So here we have a function with a side effect, which is to update sample. And it's going to be okay because sample's an array. So we have the ability to update it because it is automatically passed in by reference. We don't need to put an ampersand in front to send it in. When it comes in, we don't need to use a star to dereference it. It's already all done magically for us. Okay, is everyone happy with that? Phew.
Would it be reasonable to just have it, like not have it return something and do it by reference, but just to, if it's not solvable, say, then to return one special value by reference, like you said, every value?
Oh, no, I don't like doing that. I know what you're saying. Sometimes when we've got two different separate sorts of information coming out of a function, and the function can only return one thing, you can do this thing that I think is a bit sneaky. I used to do it, but I think it's a bit sneaky. You say, oh, I'll put both those two things together and pretend I'm just returning one thing. Like, for example, suppose you needed to remember a phone number and you needed to put a cast on your leg. Well, you could put the cast on your leg and you could write the phone number on the cast. Yeah. You can sort of combine the two things. And then someone at the other end can get the information by getting the, I need to give you the phone number. Quick, just take my cast off. Okay. You can combine two things together, but I think that's even worse than the sin of getting a function to do two things, because now in one piece of data, it has two different sorts of meaning. So I call that mixing like flow control information in with the data. And I think it's always best to keep them separate. So yes, that would be a legitimate way by C syntax of achieving it, but stylistically I think it's even worse than this side effect way. I think with this side effect way, we're at least keeping it clear that there are the two different roles. Yep. That's not to say, of course, that C itself doesn't do that. Yeah, with getChar, it'll return either the character it's read, or it'll return a special value, meaning end of file, and it returns them the same way. So whenever you read a character, you've actually got to check to see if it's control information, end of file, before you actually look and see what the character is. Yeah, C does it that way. Yep. But modern programs won't do things that way. Yep. Okay, so does everyone agree that this appears to be a solution to the problem? And look, we've got 25 minutes left. So we're finished. Except, problem solving, we better fill in some of the details. But you see, we have, I think, solved it already. But let's fill in some of the details. Well, the details are we have to write a read game, we have to write a has solution, and we have to write a show game. Let's talk about what read game would look like. Shh. Read game would be a loop. Hey guys who are talking, shh, don't talk. Read game would be a loop. It would read one character at a time. If the character's either a 1, 2, 3, 4, 5, 6, 7, 8 or 9, it will store it in the grid. Oh, I guess if the character's a dot, let's say, it will store it in the grid. And if the character's anything else, it'll just ignore it and throw it away and keep looping. And it'll keep looping and looping and looping until it's read 81 things in, and then it will stop. Does that make sense? So that's how read game's going to work. Print game's going to work like this. It's going to print out, it's going to be a loop that loops 81 times. It's going to print out the values one at a time, and every 9 values it's also going to print out a new line. Does that make sense? So it's going to print out 9, new line, the next 9, new line. So it's going to be a loop that has some sort of test in it to see if the loop counter is divisible by 9. And if the loop counter is divisible by 9, we'll print an extra new line. Does that make sense? And we'd better make sure we print a space after each thing so the numbers don't all squish together. So that's how print will work, and that's how read will work. And they sound like perfectly good lab examples to me, so let's not write them ourselves. Let's get on with the interesting one, which is has solution. Int has solution Sudoku game. Let's write him. Now notice, by the way, notice this declaration here. When we say Sudoku grid is a sample, or when sample is a Sudoku grid, sorry. When we say sample is a Sudoku grid, what we're saying is it is an array of characters. So we're declaring it. At the same time, what does the computer do? As soon as it sees this declaration, what does it do? What? It puts memory aside for it. Where's that memory going to be? In its frame. So in the frame, how many bytes will it be? Well, their characters are 1 byte each. There's 81 of them. So it'll set 81 bytes aside in the frame. So at the instant of seeing that line, not only does it tell us what type sample is, it actually creates sample. But what's sample currently filled with? Rubbish. That's right. Read game is going to overwrite all that rubbish. Read game, if you notice, is going to rely on pass by reference. It doesn't return anything, but we hope after running read game that the sample will have been magically updated and will now contain all the right values. Does that make sense? So let's write has solution. We're given a game. Now, you guys tell me, how do we solve a Sudoku game? You look for possibilities. Okay, let's play that. So we'll just grab a cell that's empty. Does everyone agree? Well, let's just grab a cell that's empty. And let's think of a value we could stick in there. If it's the only value we're in, it's even too sophisticated for me, because then I'm going to have to write things to check if something's the only value. And I reckon what I'm going to do is I'm going to pick a cell, find an empty cell somehow, and then I'm going to just stick a value in somehow. And I'm going to see if it's legal to stick that value in. I won't stick it in if it's not legal. And if it is legal, then I'm going to go and find another cell, an empty cell, and I'm going to stick a value in if it's legal. And if it's not legal, I'll try another value and another value until I find a value that's legal to stick in that cell. Now, if I've stuck a value in here 1, and then I've tried 1 in here and it wasn't legal, then I tried 2 in here and it wasn't legal, then I tried 3 in here and it wasn't legal, 4 in here and it wasn't legal, 5 in here and it wasn't legal, 6 in here it wasn't legal, 7 in here it wasn't legal, 8 in here it wasn't legal, 9 in here it wasn't legal. After trying all those, what does that tell me? It has no solution. Yeah. So I'm going to undo that and replace it with a blank cell, and I'm going to go back to the last one that I stuck in. I'm going to say, oh, maybe don't put a 1 in there, maybe put a 2 in there. Does that make sense? And then I'm going to try all the values in here again. Does that make sense? It's called brute force. It's not exactly brute force. No, it's not exactly brute force. No, we'll look at what a brute force is in a sec. So let's say how do we know when we've finished? There's no more cells. Okay. If is full, not struct. No, go back. Oh. If is full Sudoku grid. Oh no, what's the Sudoku grid called? It's called game. If the game is full, then what do I know? Yeah, it's called sample, thank you. If the no, it's called game. It's called game here. If the game is full, then what do I know? It's done. I better define solved. So if is full is true, and solved equals true, and at the end, I'm going to return solved. Okay. If it's not full, then what am I going to do? I'm going to find a candidate cell. And what does this candidate cell have to be? Has to be blank. A candidate cell can be next empty. Well, it might not be next empty. I don't care which empty cell it is, just an empty cell. No, maybe I should, maybe I shouldn't. I don't know, I just need to find an empty cell. Okay? After we've written this and it's working, then I might decide, oh, I'll do it this way rather than that way and it'll speed up. But let's just get it working. So an empty cell, how do you spell cell? Get me an empty cell. Well, if it's getting me something, I always like to name my functions with a verb because they're doing a job. So get me an empty cell. Get empty cell. Stop doing that. Oh, I got to stop doing that. All right, get me an empty cell. Oh, what's candidate cell? What type is candidate cell? It's a cell. Okay, I'm going to get me an empty cell. Then what am I going to do? What did I say we're going to do? We're going to find an empty cell and we're going to stick in a value. What am I going to call the value? Equals trial value, maybe? I'm going to say the trial value no, well, I don't like while loops. No. What's that?
Cell candidate cell that value trial value, not value equal.
Line 34.
Line 34. Oh, yeah, thank you. Value doesn't equal. Oh, yeah. That's weird. That's weird. A type equals a variable, can't do that. Variable equals type, can't do that. Trial value equals what value? A random one. But that's too much work. I don't want to generate a random one. 1. Aha, equals 1. Let's try the first one first, and let's just try all the values one at a time. Oh, actually, it's got to be a character one. Oh, actually, didn't I define something there? I think I called it min something. Min value. I think that's defined to be 1. Let's have a look up the top. Yeah, that's right. And min values, if you look at it, a char, the character 1. Okay, so we're going to go, our trial value is the smallest value. So we've picked a cell, we've picked a value. What do we have to check now? If what? Yeah, if it's legal to put it in there. If is legal, if it's legal to stick in the game, in that cell, in the candidate cell, if it's legal to stick in the trial value, if that's the case, then what am I going to do? Stick it in. So I'm going to set the cell in the game, in the candidate cell, I'm going to set it to be trial value. Whew. All right, how's that looking so far? So we've set the cell. What if it wasn't legal? Oh, I know. We've set the cell, and now what do we need to do? So I've set the cell, I've put like the number 1 in here. Now what do I need to do? I don't want to loop. What do I have to do? I've got a Sudoku grid which is partially filled in. What do I want to find out? I want to find if it can be solved. I want to solve the new grid that I've got. So if has solution game. So I've stuck in that value. Now if what I've got now has a solution, I'm happy as can be. Solved equals what if it doesn't have a solution? What do I have to do then? What's that? I've stuck 2 in here and I've discovered there is no solution for the rest of the grid with a 2 in there. I need to change this to, yeah. I need to I do need a while loop, don't I? I'm going to have to try all the values one at a time. While it hasn't been solved and trial value, what did you say? Trial value? Trial value is less than or equal to max I better initialize. Okay. So here's what we're going to do. Let's just look at the code. Let's just collect our thoughts. I think we're nearly there. If the game is full, we return solved and we're done. If the game is not full, then we pick a candidate cell. We pick an initial value to try in that cell. We notice that we're not yet solved. And then until we become solved, or until we run out of trial values to stick in, we repeatedly try to set the cell to the trial value. And then if there is a solution, solved is true. And if there isn't a solution, what do we have to do? We need to set the cell back to blank. Oh yeah, thank you very much. Okay. We're going to repeatedly. Oh, hang on. Oh, what did I do there? If it's legal, okay. We've got a trial value and a trial location to stick it in. If it's legal to stick the trial value into the trial location, then we'll do it. Set the trial value into the trial location. And if there is a solution with this new configuration, then we're done. Otherwise we need to, what? Reset somehow. Clear cell. We need to clear the cell we've just put in. And we need to, what? We need to increase the trial value. Yes, thank you very much. That's probably good enough now. If it's legal, and then regardless of whether it was legal or not, let's increase the trial value. Whew, how's that looking? Does that look good? I think we got it. I need to what? Oh, no, this does. Let me show you how it works. Let me just, we won't be able to compile it because we haven't written a lot of these little functions. We've got 5 minutes, I think we're run. We'll get there. First of all, can I just talk about the process we went through there? Because there was a bit of sort of frantic coding and you might have just been aimlessly staring at the screen while I was doing it. What we did was we worked out, first of all, how we were going to represent the game. We then wrote a very high-level function to solve it. And we saw all we needed to do was read it in check if it had a solution, and print it out if it had a solution. So that was a very high level solution, but we relaxed. And then we thought, okay, let's zoom in on the next big chunk. And the next big chunk is the thing that works out simultaneously if it has a solution, and if it has a solution, it finds it. And we did that very simply using recursion. What we did was we noticed that we just had to find an empty cell. We stuck a value in it, and we saw if the rest of the grid could be solved. Because remember, this is seeing if a half-filled-in grid can be solved, is our puzzle. So we fill in one more cell, it's still a half-filled-in grid. We ask recursively, can it be solved? If it can, then we found a solution. If it can't, then we don't know if it couldn't because it was the value we stuck in last of all, or if there was no solution regardless of what value we stuck in there. So inside the loop, we one by one tried all the possible values in this spot. And every time we stuck a value into this spot, we asked if it could solve the rest. And at any point, if it said it could, we broke out of the loop and returned true and said we're done. But if it couldn't, no matter what value we stuck in there, if it couldn't solve the problem, then we say, oh, well, we're stuffed. There is no solution. Does that make sense? And we clear this cell out. And we abort. And we say there's no solution. Does that make sense? Okay. That is the recursive solution to this problem. All that we need now is to define a few functions. Because this is a top-down design, we've discharged a whole lot of small functions on the way we have to write. Is it legal to put a cell here? How to find an empty cell? How to set a value in a cell? You know how to do all this. It's all very easy. How do you set a value in a cell? You write it into the array in that location. How do you get the value from the cell? You read it from the array at that location. How do you clear a cell? You write empty value at that location. How do you find an empty cell? You loop through all the cells with a while loop until you find one that contains empty cell, and you return that. All of these functions are quite trivial. You could write them very easily. In fact, I did before I came here today. And I stuck them in a function called Sudoku grid.h. And that contains in it all the functions that we've just defined then. It also contains these type defs, so I'm going to pull them out now. Now let's compile it and see if we've got it all right. I think the includes, okay. I just got to look for my compiler. With hash include, guys, don't you remember, if you put angle brackets around it, it loads in a system.h file. If you put quote marks around it, it loads in a file that you've written yourself in the current directory. So I've written it myself. Do you want to look at what Sudoku grid looks like? File, open, Sudoku grid.h. Here's what it looks like. It just contains all that stuff here, plus all the functions. Prototypes for all the functions. Set cell, get cell, clear cell, is full, free cell, get free cell, is legal. Now if we happen to call all the functions the same names, and if I haven't made any typos in here, we should now be able to compile this. If I can work out how to find that window. Here we go. Build. Did it work? 2 errors. Let's find out what they are, because we've only got seconds left. True, undeclared. Oh, I haven't defined true or false. Oh, okay, let's define true and false. How would you define true? Hash define true. 13. You could. No, semicolon. No. Hash define false 0. All right, let's build it again. There'll be a few compile errors, but hopefully we've got enough time. I still found 2 errors. Empty, get empty cell. Oh, we called it get free cell, did we? Oh, let's fix that up. Get empty cell, get free cell. Ha 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 ha. Build succeeded, it worked. All right, shall we run it? Oh, now, before I run it, do you guys see now that to solve this problem, all we needed was to work out a very top-level way of solving it, work out the right data structures, work out some simple functions on those data structures that arose naturally as we were writing the solution, rather than trying to solve lots of complicated things at the bottom and join them together to make a solution. This is your task 2. Your task 2 is to write those small functions. Plugged into the code we just wrote then, it will solve a Sudoku. I've done one in advance. Let's run it and check that it does solve the Sudoku. And where is it? It's in this directory. Oh, we've only got seconds left. Can someone remember this? Users Richard B. sample code Sudoku build release. Whew, that's the world's longest path. Let's go. CD. What was it? Oh, was it users? No, I'm in users. 1917. Hang on, don't call that now, because I want to be fast. Sample code. Was it Sudoku? Build. Release. Whew, thank you very much. LS, there it all is there. I've got 2 sample grids here. Let's go show you what they look like. Here's grid 1.txt. Oh. Okay, let's just run Sudoku. It's waiting for me to type a grid in, so let's just stick a grid in, and we're going to stick in a completely empty grid. I've got to put in 81 of these. But remember, the way we're writing read is it's going to stop after it's read 81 of them. So if I put more than 81 in, it'll forgive me. Can someone work out how many I'm sticking in? Do I need the spaces? Oh, no, I don't. Look, that's got to be enough, doesn't it? Oh, I kept reading. Oh, all right. Curses. We've been foiled by time. This does run. I ran it last night. It is your assignment. The assignment spec is now released. Go for it, guys, and we'll run it live on Wednesday to show you how it works.